Hello and welcome everyone to Chemistry 101 again, General Chemistry 1. It's your instructor Ismail Badran speaking, and today we are going to continue with Chapter 2 and finish actually Chapter 2 with the nomenclature. And as we said last time, just a quick refreshment of your mind on the nomenclature of chemical compounds. Before you name a chemical compound, you have to ask yourself if it is what type of compound do you have. Compounds usually they are either ionic or covalent. So sometimes they call them molecular compounds. And we said that last time, but we just need to refresh again. Ionic is composed of a cation plus an ion. So for example, or like something a metal or non-metal. So for example, that would be for example NaCl, table salt. That's a metal and a non-metal making a compound. So that must be ionic. Let's say MgSO4, magnesium sulfate. That's a cation, which is magnesium, and a sulfate group. So that's also ionic compound. It has different rules of naming. Covalent compounds or molecular compounds. They're usually a non-metal plus non-metal, or non-metal plus hydrogen. So water, for example, is a covalent compound or molecular compound. Let's say CO2. All the oxides are not all oxides, most of the oxides are. So CO2, let's say Si, Br4, whatever. These are all molecular compounds because they are composed of non-metal plus non-metal or non-metal plus hydrogen. So last time we also talked about different rules to name ionic compounds. And there is type 1 and type 2. Type 1 contains group 1 and 2. In addition to silver, cadmium, and zinc. Type 2 compounds, type 2 ionic compounds, they involve transition metals in them. So if you wanna ever to name this compound CaCO3, first you wanna think about what is this coming from. I know this is a carbonate group, CO3 2 minus. Ca calcium is in group 2, so it must have a 2 plus on it. It always make 2 plus. So that's good, 2 minus 2 plus, that means they are balancing themselves. And this is a type 1 because of the fact this is calcium. Calcium is in group 2 of the periodic table, so just name it calcium carbonate. There is no need to mention any number or any Roman number or anything like that, just calcium carbonate. If I'm asking what is calcium carbonate, you will say CaCO3. This is different. This is CaCO3. This is a small O, not a capital O. So this is not carbon oxide. This is a cobalt. If you look at the periodic table, you will see cobalt in the middle of transition metal. So, but you don't know what is the charge of cobalt because cobalt itself makes more than one. Again, I am sure about this. So CO3 2 minus. You start from what is certain. You're sure about this 2 minus. So that must be making a CO2 plus. Nothing else. Then you say it cobalt carbonate. But if you name it like that, it is wrong. In a type 2, this is type 2, you have to put the charge of the metal as a Roman number. So this is type 2, this is cobalt 2 carbonate, or you can add brackets here if you like. So cobalt 2 carbonate, that's CaCO3. If we have been asked what is nickel 2 nitrate and iron 3 phosphate, now I'm giving you the name, you should write the formula. This is even easier because I know this is nitrate, so that must be NO3 minus. Nickel 2, what is nickel 2? That's nickel 2, like that, 2 plus. So we have different charges here. We have different charges, so we need to cross multiply. So minus 1, so that's 1. Okay, or you can do that like that one, plus 2, cross multiply, and it becomes Ni1, NO3, 2, but this is a group, so you have to put it in brackets like that. So nickel 2 nitrate is NiNO3O2. Iron 3 phosphate, again, iron is Fe, and it says 3, so it must be 3 plus. And phosphate is the group which is PO4 3 minus. You should memorize that. Again, you have different charges here. So you cross multiply and it becomes Fe3 PO4, all three, but this is an ionic compound, and therefore you simplify this into FePO4. So that's iron 3 phosphate, FePO4. And from this you can tell that this is a 3 minus group. Okay, so this must be 3 plus. So this is the correct formula of iron phosphate, just FePO4. Now moving into covalent compounds, and CCl4 is one example of a covalent compound or molecular compound. The reason for that is carbon is a nonmetal, also chlorine is a nonmetal. So you don't name it according to the ionic compounds rules. You have to go with the covalent compounds rules. So you use mono, di, and tri, and tetra, and all of these prefixes. So you can name this mono carbon tetrachloride. That's another tetrachloride. But usually we drop out from the mono. So it's carbon tetrachloride. Carbon tetrachloride is the name for CCl4, which is a common solvent in chemistry. SiO2. So again, if you name this silicon oxide, that's going to be very misleading because I don't know which silicon oxide you're talking about. This is a covalent compound. Okay, silicon is non-metal, or it's actually a metalloid, but we deal with it as a non-metal. And this is also a non-metal, so this name would be wrong. The correct name for this is monosilicon dioxide or silicon dioxide. So this is silicon dioxide, dioxide, or just name it dioxide. Okay, the problem with this is they start mixing between things, okay? They start mixing between type 1 and type 2 and the covalent compounds, so be careful about that when you name things, okay? When you name things. An example would be, let's say this, Na3N, okay? N3N. Now, people might have the mistake and they think this is a covalent compound, so they call it sodium. Let's say this is, okay, just like that. Trisodium mononitride, let's say, okay? Because this is a mistake, this is a big mistake. This is not called trisodium mononitride because of the fact this is an ionic compound. This is not a covalent compound. Sodium is a metal, it's a group 1. Nitrogen is non-metal, so this is indeed ionic compound. It's type 1, and therefore the correct name for this is just sodium nitride. Sodium nitride. So this is wrong, and the correct name is sodium nitride for that one. So moving on to the story of acids and bases, which is the topic of today's lecture. HCl actually is a gas, so we can just write here G for a gas. And when it's first manufactured, it's actually a gas. You can just Google this if you want to learn anything. You can just Google it. Here I write down HCl gas, and it says here, you see these cylinders that they contain HCl gas. It comes in big cylinders, industrial gas cylinders. If you want to name this, you want to ask yourself again if this is ionic or covalent. Anything with hydrogen would be covalent for me. So I will say this is called hydrogen chloride. You can argue it's hydrogen monochloride, but it's known for hydrogen chloride. But that's in the gas phase. If you ever drop this into water, okay, HCl will dissociate completely, and it's going to form ions of H plus and Cl minus. So there is no HCl anymore. There is no HCl gas anymore. It's now all ions. And now we can refer to this by HCl aqueous, AQ for aqueous. Now it has a different name. This is called hydrochloric acid. Hydrochloric acid. Okay? And same as this, same as HBr is follow the same story. So our topic today is about acids and bases. An acid is a substance that yields hydrogen ions when dissolved in water. So usually the molecular form of an acid starts with H, so HCl, HBr, HNO3, etc. And when a substance is dissolved in water, it's referred to as an aqueous solution. Ac written after the formula of the compound. For example, HCl aqueous. Formulas of acids contain one or more H atoms and an ionic group. So this is explained again in this slide what is happening with HCl. When you put it in water, it forms H3 plus ions or H plus ions and the Cl minus, and now it has a different name. There are actually two types of acids. There are the binary acids, just like HCl, HBr, and those things. H2S would be one of them. And oxy acids. Oxy acids, they contain oxygen on them. An example of an oxy acid. So how do we name acids? First, binary acids, they named as hydro. Okay, if they are an aqueous solution, they're named as a hydro, and then the base name of the nonmetal, and then ec. Okay, and then acid. So I say hydrochloric acid, hydrobromic acid, hydrofluoric acid, and so on. For example, for H2S, we have a sulfide, so it's hydrosulfuric acid. Hydrosulfuric acid. Again, this slide shows you the name of the pure compound, in other case in the gas phase. So if HBr is in the gas phase or it's in a pure compound, it's not mixed in water, it's called hydrogen bromide. But when it's in water, you call it hydrobromic acid. Same thing as HCl and HI. For naming oxy acids, we have two rules. If the anion is 8, like nitrate or phosphate, we convert that to IC, so ec. So nitrate becomes nitric and phosphate becomes phosphoric. If there is an ITE in the end of the anion, so let's say nitrite, it becomes OUS, so us. So nitrate, nitrous. There is phosphate, but there is also phosphite. Sorry, there is sulfate and sulfite. So sulfite would be sulfurous. Okay. So here's how you name this. You take the name of the acid, and if it's 8, you make it IC. If it's IT, you make it OS. An example of that is H2SO4. H2SO4 contains the ion, which is SO4 minus, which is sulfate, okay, and therefore it's called sulfuric acid. So sulfate, sulfuric acid. On the other hand, we have another acid, which is H2SO3. H2SO3 contains the SO3 minus ion, which is sulfite, and therefore the it goes to us, and it becomes sulfurous acid. So this is how you differentiate between the two. Other example would be nitrate and nitric acid, for example. Nitric acid is HNO3, and nitrous acid it's HNO2. Here are a few more examples. So nitric acid HNO3, and we name it because NO3 is nitrate, or NO3 minus is nitrate, it becomes nitric acid. We have H2CO3, CO3 2 minus is carbonated group, so it becomes carbonic acid. And similarly phosphoric acid because of the phosphate. Here we have another examples of polyatomic ions, which are the chlorates group. So we have these four groups, which are the chlorates group. The first one is ClO4 minus. They all actually contain the -1 charge. But they are different in name. ClO4 minus is called perchlorate, ClO3 minus would be chlorate, and ClO2 minus would be chlorite, and ClO minus would be hyperchlorite. So you can make salts out of this. So for example, this one here, NaClO, which is the same as actually NaOCl. This is the sodium hypochlorite, which is the bleach, the one we use in houses. So this is actually a bleach. If somebody asks you what is bleach, you can just say it's sodium hypochlorite, okay? You can say NaClO4, that would be sodium perchlorate, okay? But since we are talking about acids and bases, these ones actually makes acids. So we have 4 acids here. We have HClO4. We have also HClO3. We have also HClO3. We have HClO. We have HClO2. Let me just clean this for now. And we have also HClO. So remember the rule that 8 becomes IC and I becomes OS. Okay. So if you want to name this as an acid, this is called perchlorate. So this would be perchloric acid. This is a chlorate, so simply it's a chloric acid. I'm just changing the 8 into IC. This is chloride, so the chlorous acid. And hypochlorite, that means hypochlorous acid. Hypochlorous acid. Okay? Now, one might ask the question, what would be this acid called? Let's say. Now, is there such thing? Maybe. Well, if you wanna think about this one contains H plus, okay, and this group BrO2 minus. Now we don't have BrO2 minus in the chemistry 101 in the syllabus, but I mean, if you want to think about it, BrO2 minus would be just similar to ClO2 minus, because I'm just replacing Cl with Br here. So this is called chlorite, and therefore this would be bromide. Okay, bromide. This is the bromide group. Let me write it down. Bromide. And if I want to make an acid out of this, I would just call it bromic acid. Bromous acid. Bromous acid. See that? It's simple. Because the I becomes us. Bromous acid. There are some other examples of that, of course. So that's explained all in this slide. Actually, HBrO3 and those things are in the syllabus. So you can take a look at this slide by yourself. There's a few more examples here for naming acids. And this is also a summary of what I was talking about. Remember, perchlorate, chlorate, chloride, and hypochlorite. This is how you name them. There's also a bunch of common acids here. They are basically a repetition of what we said before. The one we didn't talk about is acetate. It becomes acetic acid. That's the vinegar that you use in the kitchen. Okay, so the CH3COH. This one is an organic acid. That's why the H appears at the end, and it comes from the acetate ion. That's why it's called acetic acid. There's carbonate group that makes it's CO3 2 minus. If you want to add hydrogen to that, you need 2 hydrogens. It becomes H2CO3. That's carbonic acid. Carbonic acid. That's in the Coca-Cola, and some other ones. So the best example, of course, is sodium hydroxide, which is widely known, and it's used widely in industry and to make soap, known as lye. So lye is sodium hydroxide, which is NOH. They have also KOH. You see here, OH is the OH minus group that has 1 charge. So it combines with a metal from group 1. It's 1 to 1. So we have KOH. It's not K2OH or KOH2 or anything like that. But when we have something from group 2, like barium, OH has -1, Ba has 2 plus. If you cross multiply, that would be BaOH2. But we'll still call it barium hydroxide. We never call it barium dihydroxide, or let's say barium 2 hydroxide, because this is type 1. Again, the naming here is important. Well, ammonia. What about ammonia? Ammonia is an exception. Ammonia is a molecular compound in the gaseous or pure liquid state. Is also classified as a common base, but it's actually a weak base, and we're gonna talk about weak bases and strong bases later on. And ammonia is a base because it actually yields OH minus in water, okay? And we're gonna also talk about that in the future. The last thing in this chapter is something called hydrate. Take for example CSO4.5H2O. This is a hydrate is a compound that have a specific number of water molecules attached to them. So, for example, you are working in a company or something, and you call the supplier and you say, "I wanna buy 5 kilograms of copper sulfate," and the salesman on the other side he says, "What copper sulfate do you need? Do you need the anhydrous or the hydrous one? Do you need the hydrated or the anhydrous?" The anhydrous copper sulfate, that's a pure copper sulfate. Probably it's expensive because it contains no water on it. Okay, copper sulfate, CuSO4. But copper sulfate commercially, it's available widely as a hydrate, because copper sulfate absorbs water from the atmosphere. So water molecules is attached to the structure, and depending on the size of the molecule, specific numbers of water molecules attached to that. In this case, we have 5. So these 5 water molecules are actually connected to the to the CuSO4 crystal, and we call this a hydrate, okay? And we use the prefixes mono, di, or tri, or etc. to mention the numbers of water. So CuSO4 5H2O would be copper sulfate pentahydrate, copper sulfate pentahydrate. We can, in order to, if you like to get the water out, you just heat the stuff in the lab, okay? You put this in a crucible or a container, and you heat it up. Water will evaporate, leaving the CuSO4 by itself. In this case, we call it anhydrous copper sulfate. That means it's is without water. I just made a mistake here. This is copper 2 sulfate because it's a type 2 compound. Similarly, we have BaCl2, 2H2O, that's called barium chloride dihydrate, because there are two types of water here. And another one is LiClH2O, that's lithium chloride monohydrate. We must put the mono here in order to mention the number of water molecules. So that's about hydrates, that's another example. So by this, I would like to thank everyone who listened to my lectures and follow up in chapter 2. So this is a summary of all the rules that we have. I wish that you can practice this either by the online assignments or the quizzes in the book and so on. And we will have a chance to also practice this in the lectures. So thank you so much and have a beautiful day.